Hey, good morning, those of you who are close to EST. Welcome to the 13th session of the RQI-Online 2020-2021. This session will begin with our first speaker. That is Professor Jorma Loco from the University of Nottingham. Jorma, can you share screen?
I can try. Okay. And
all right, there we go. So Jorma is going to tell us about how thermal is circular acceleration. Jorma, okay. Floor is yours whenever you want.
Thank you very much. Can I check, is the picture looking okay to you?
Yeah, it is.
Okay, but I can't move back and forth, so I should do something else.
So yeah, you can now.
Okay, so is it okay for you?
Mm-hmm.
Thank you very much. Yes, so thank you very much for the scientific organizers of this meeting for the invitation to speak. There is a well-known observation that in a meeting with a coherent theme, it's good to have your talk scheduled towards the end, because that way you can mostly skip the introduction. Today I am keenly aware that today I can almost also skip the conclusions. This has been a meeting with a fairly, or this continues to be a meeting with a fairly coherent theme. And there have been many talks about the Unruh effect, Fulling-Davis-Unruh effect, and that is the topic of my talk today. So the title is How Thermal is Circular Acceleration. We are familiar, we first learn about the Unruh effect in the context of linear acceleration, but there is a similar effect for other accelerations, including circular. And it's the circular acceleration that I want to address today. There have been many talks related to this topic at this meeting, and the stage has basically been set, and most of the conclusions have been made already. I want to focus on a certain piece of material there in between. This question, how thermal is circular acceleration really? And here's the plan. So even though this topic is familiar to many and we've heard lots of talks, I should start by setting the stage, because I want to appreciate the focus of the actual results that I'm going to present and the limitations that go into those results. So I will need to do some introductory material with that point of view here. So I'll first recall a few facts about the Unruh effect, both in relativistic spacetime and in analog spacetime for prospective experiments. And then the device that I'm going to be analyzing. And then I'll recall a few facts about circular motion. And specifically, I want to highlight what is different in circular motion in different spacetime dimensions. I want to consider both 3+1, our home universe case, and the 2+1 case, which we think is going to be relevant for the laboratory experiments in the analog setting. And with all of that preparatory material there, I will then give some results answering this question in this setting: how thermal is the circular motion? That is the circular motion temperature, which I will define in due course. How close is it to the linear acceleration Unruh temperature? I'll be considering this ratio. And at the end, I'll summarize and discuss where one should go next from here. Now, when we do these talks live, this would usually be a good moment to stop and ask if there are any immediate questions. I understand that the present format is not well suited for this, but if you have some thoughts at the moment, feel free to jot them down now and bring them up at the end when we have the official question period. Right, so Unruh effect, well-established physics, we would say, going back to the 1970s, and the basic observation is if you do relativistic quantum field theory in Minkowski space, you put the field in its usual Minkowski vacuum, no particle state, and you linearly accelerate there, then you perceive the vacuum state in a certain sense as if it was a thermal state in a temperature proportional to the acceleration. And the way you see this by using your local equipment is you look at excitations and de-excitations in your equipment. You might think that you have some jar of beryllium atoms and then some jar of lithium atoms, and you look at them once in a while and see what fraction is an excited state and what is not. And you look at those excitation and de-excitation populations, and the prediction is this has the characteristic of something thermal. The ratio is exponential in the energy gap divided by temperature. And it's a temperature there that you can operationally measure, and that gives you this formula here, acceleration over 2 pi. There are some limitations into the standard formula, which I've listed here, like weak coupling, long time, and the significant subtlety there. But those subtleties are not the topic of this talk. So this is a real effect. Eh? It's so real that you can cook a steak with it. You really do cause excitations in your local systems. But to date, no steaks have been cooked with this effect for when we put in the numbers, the constants of nature. We see that there's h bar here. It's a small number in everyday units upstairs, and then there's the speed of light, and it's a large number in everyday units, and that's in the denominator. So it says to get 1 Kelvin temperature, you would need 10 to 20 meters per second acceleration and so on. So in this relativistic space-time setting, no observation to date. Some thoughts on how this might be made observable in the relativistic setting, but no observation to date. Right, now we have heard at this meeting that there is interest in trying to simulate this motion in a laboratory. Okay? And linear acceleration has problems for that thing. If you accelerate linearly, you will hit the wall of your lab at some point. And I'd like to concentrate on circular motion, and it certainly has a circular uniform motion, and it certainly has the advantage that you can stay in a finite size lab, finite size inertial lab, if you wish, for an arbitrarily long time. You just keep going on circles and circles and circles. And this idea, in fact, goes back to the 80s to work by Bell and Lainos and subsequent developments, where they thought that accelerator storage rings might provide a test of the circular motion Unruh effect over there. Now, this idea has limitations because in those accelerator storage rings, there's a sort of limited number of data points that you could hope to measure. And Bill Unruh was talking about that earlier in this, was reviewing that earlier in this meeting. But what is now more acute for us, more contemporary for us, is that there is this analog space-time program where we have effectively relativistic field equations. And so it could be Bose-Einstein condensate, it could be some superfluid helium. We've had many talks at this meeting about this. So I'd like to address this circular motion in a way that is adaptable, that is applicable to this analog space-time setting. And I want to address what is the sense of temperature that you would see in these measurements. Okay, so why now? This is prompted by the experimental proposal that Bill Unruh was describing. It is an analog spacetime experimental proposal using perhaps Bose-Einstein condensate in the primary version, possibly adaptable to some superfluid helium system. Well, I will not describe that experiment again, but the crucial points about that I've listed. So first of all, this experiment uses the fact that we have a finite size lab, and if you want to build a Bose-Einstein condensate, it will be a very finite size thing. Okay? The second thing this circular motion experiment utilizes is a time dilation effect. Now, if you have some Gross-Pitayevsky equation describing your Bose-Einstein, and then in some limit you get an effective relativistic field equation out of it. Okay, so that's a relativistic field equation, and that's one ingredient in the Unruh effect. But there's a second ingredient in the Unruh effect, and that's time dilation. Okay, and time dilation does not exist in Bose-Einstein condensate. It does not exist in superfluid helium. So if you are proposing to do this experiment with an analog system, you have to ask, how are you going to factor in the time dilation in your system? And with linear acceleration, this is a problem because, well, time dilation in linear acceleration, it's not constant in time. There are some experimental proposals of how you might be able to mimic this time dilation in linear acceleration if you somehow engineer strongly time-dependent couplings in your system, exponentially changing time-dependent couplings. There are some thoughts, but it's tricky. With circular acceleration, time dilation, well, it's constant in time. Okay? So if you want to describe this relativistic time dilation in a laboratory system that does not have time dilation, you don't need to put in any physical system there that would factor in the gamma factors. The gamma factor you can do entirely at the data analysis level. You measure what you measure with respect to your lab times, with respect to your lab energies, and at the end, when you analyze that data, you compare with the Unruh effect prediction. Well, you put in the relevant gamma factors at the data analysis level. So these are two strong selling points for using circular acceleration in the laboratory setting. So what today? Right. So today I am going to imagine that we order from an online store a quantum dot, some sort of localized quantum system, very localized quantum system, and then we put that localized quantum system on a circular orbit in our Bose-Einstein condensate, or maybe in our superfluid helium and something. Okay? And we ask, what are the excitations and de-excitations that happen in this quantum dot? That's the theoretical setting that has been around since the 70s. That is the theoretical setting with which I am going to address this question of the circular motion Unruh temperature today. There are these questions of finite time and so on, which I brushed under the carpet on the previous overhead. I'm not going to address them here either. They are subject for future work. I am making the usual assumptions that we're in the weekly coupled regime. We are operating the system for a long time, negligible switching effects. We're basically thinking that it's a stationary system. Okay. And the question I want to ask is this temperature. What is the ratio of the actual circular motion Unruh temperature to the temperature that you would expect if you had linear motion? And I want to do this in a way that handles both a relativistic space-time and the analog space-time that we have in the back of our mind here. And I want to do it both in our home dimension 3+1 and in 2+1. What we'll not do today is, right, so I'm imagining that we order a quantum dot from an online store. Was not available last time I checked. And in fact, the experiment that Bill Unruh was describing the other week, it does not postulate a quantum dot. It uses lasers that we actually know how to build and order from your favorite online store, and use that laser to gather some correlations out of your quantum system. How the quantum dot results relate to the actual experimental scenario, that is not a topic for today. That is a topic for future work. I should say a few things about this quantum dot. Now, this is material that is, of course, familiar to many. I mean, they are so quantum dot is words that are familiar to the solid state community. And in the relativity-based community, we would talk about the Unruh with detectors. But I should set some of the notation up. So I want to make the point that there are some things that are dimension independent, and some things that are dimension dependent. And I want to build towards the point where things do become dimension dependent. So I want to build, so that is the idea behind this technical background that I'm going to review. So my quantum field standard setting, right? Space-time dimension, I'll keep it general for the moment. My field is a real scalar field. At some point, I'll make it massless, but for the moment, it doesn't need to be. And I've prepared the system in its usual Minkowski vacuum. And this quantum dot, I'll think of it as a two-state system. Point-like, so spatially point-like, moving on a world line there. Two states, the state 0, state called 1, and the energy difference is E. Positive E means 1 is the excited state, negative E means 1 is the ground state, and so on. And right, so I'm saying two-state detector. And that's, of course, a limitation. You might say, oh, well, why don't you use a harmonic oscillator? For what I'm going to do, you could just as well do this with a harmonic oscillator. I'll be doing first-order perturbation theory, and there it doesn't matter whether you have a two-state system or harmonic oscillator or some system with many states. It's only the energy gap in a transition that is going to be relevant here. So that's standard setting. Standard interaction, point-like interaction, right, over there with some coupling constant in which I'm doing perturbation theory, some function that tells how this interaction is switched on and off, and then something that describes the internal degrees of freedom of that detector. So if we thought of that as a poor man's atom, then this mu would be the thing that carries the information about the atomic orbitals and their shape. And that's going to be largely irrelevant for us. And in this standard setting, we now ask for the probability of transition. You start with the field in its Minkowski vacuum. You start with your quantum dot in the state 0. And then you ask for a probability of a transition in the detector to have happened, and you don't observe what is happening to the quantum field. You only look at the detector. And a calculation says to first order perturbation theory, there's the coupling constant squared, then there's detector internals, which will drop from now. And then all the interesting things are in this thing called the response function, for which we have a formula. It's a double Fourier transform over the Whiteman function, the two-point correlator of your quantum field pulled to the world line. Okay. So there is the piece that knows about the energy gap. There is the piece that knows how your detector has been turned on and off. And here is the thing that we are really interested in. This is the quantum input, information about the quantum state, in this case, the Minkowski vacuum. and the pullback of how you probe that quantum state on your trajectory. And right, so we are talking about distributions, of course. So if you like to think in terms of an I epsilon, there's an I epsilon hit somewhere in the formulas. But let me assure you, the distributional things are here entirely straightforward. So no sins have been hidden in the I epsilon. Right, so that's quite general, any motion. I want to consider stationary motion. Circular stationary motion is certainly one example of a stationary motion, okay? Then I want to look at the long time limit. And so there's a big business here in its own right with talks in its own right. But I will just pass to the long time limit in which this switching effect is negligible. And then we have a stationary response function over there, and that knows about the Whiteman function. Now it's a simple Fourier transform of the Whiteman function pulled back to the world line. Okay. So this now tells what the transition rate is. For positive E, it's the transition rate upwards. For negative E, it's the transition rate downwards. And this formula tells us what we see in the jars. If we want to describe this by a temperature, the formula I want to use for temperature is over here. Okay, some logarithms. Why is that the formula I want to use to define a temperature? Well, if you had a genuine thermal state, Kubo-Martin-Schwinger state, this would in fact be the temperature parameter describing the Kubo-Martin-Schwinger state, right? Call it detailed balance and so on. And in this case of linear acceleration, this formula produces us this energy independent number A over 2 pi. So this is the detector, the quantum dot calculation that tells us in linear acceleration, the Unruh temperature is over here. For circular motion or for other uniform motions, so you can certainly calculate this. It might now depend on other things than the acceleration, other parameters of the orbit. It might also depend on the energy. And this is an observation that goes back to the 80s. And recently, Benito Juarez Aubry was telling about how this temperature depends on the energy in different types of trajectories. And right, so there's a whole zoo of these stationary trajectories that you can consider in 3+1 Minkowski. But I will consider the circular one. The selling point is I want to keep it in a finite box for an arbitrary long time. So here's what I want to calculate, and I want to calculate it for circular motion. So Minkowski spacetime, I'm doing it in the relativistic setting for now. I'll comment on the translation to the non-relativistic setting in a few moments. So we know how to write down a circular trajectory. It's relativistic, so there are some gamma factors there, but 2 parameters suffice. So I could take the radius to be one parameter, and the other parameter I could take to be the orbital velocity, so between 0 and 1. And up to now, things have been fairly independent of what the dimension of the space-time is, whether the field might have mass, for example. Now is the moment when I want to specify to 3+1 and 2 dimension, and I'll also specialize now to the massless field. And here are the explicit expressions for this Whiteman function pulled back to the world line. Okay, so it is, as we know, in 4 space-time dimensions, the Whiteman function, it is 1 over delta x squared, the space-time proper distance squared, and there it is expressed on this world line. Okay, so that's a familiar expression. If you go to other dimensions, staying 3 or greater, then the only thing that changes is the exponent over here. Okay? So each dimension that you add or subtract brings you down by a square, up or down by a square root. And I'm interested in the 2+1 case. So in 2+1 case, that square, it becomes the square root of a square. Okay. So things are different in different dimensions. And this is the difference I am interested in, especially if at the end of the day I want to talk to an experimentalist who has a system with two spatial dimensions. So let's examine now. Let's get the calculation going. Calculate this circular motion detailed balance temperature and compare it to what you'd have in linear acceleration. For the sake of comparison, I'll do it with the same value of proper acceleration. Okay. And then go and do the same thing in analog space-time by putting in the relevant gamma factors when translating the definitions of temperature, the definitions of energy, and so on. So that is our task. One final comment about this overhead. So let's stare at these two expressions over here. So this is the familiar 3+1 dimensional expression. And so it's delta x squared, and delta x squared, well, it can be positive or negative. On a time-like trajectory, it is in fact negative, but for real, for non-zero s, this is certainly a real number. There is the I epsilon that takes care of this coincidence limit singularity, but for real s, this is a real number. Consider the 2+1 dimension case. I've got a real negative number under the square root, and then I take the square root. Presumably I'm going to get an imaginary number out of it. And I am, but it's still okay. So the Whiteman function needs to have the property that if you send s to minus s, the Whiteman function goes to its complex conjugate, and that's okay. You are positive imaginary with one sign of s, negative imaginary with the other sign of s, and this is perfectly okay. It's not a problem for the quantum field theory that you have here something that that is imaginary or complex. But it will become an issue towards the very end of the talk. So let's store that observation for discussion. And now I think all the background is in place, and I can start showing what we find. Okay, so let's do first the relativistic space-time, 3+1 and 2+1. Right, so it's a 30-page paper, and we do analytically lots of limits, and then we do some plots. Let's start today with the artistic impression, and then work our way towards the some of the technical merits. So,
hey, Jorma, is this 5-minute warning?
Thank you. Here is the picture. So this is the relativistic space-time. What is plotted is the circular motion temperature that we calculate, divided by the linear motion temperature that you'd expect, that you'd have same linear motion. That's on the vertical axis of these plots. Now, for some reason, I called it T-rat, rat meaning ratio. Okay, poor terminology, but that's what's on here. Then I want to plot it as a function of the velocity. The orbital velocity is over here, okay? And then as a function of energy, and energy is a dimensionful quantity, so I want to normalize it somehow. I'm normalizing it to the proper acceleration. This is the dimensionless number, and this is a sensible number to consider, or sensible normalization to look at here, because we know that in the linear acceleration case, it's really this E over A that enters the formulas. So, ladies and gentlemen, here's the plots. And by immediate inspection, you see this ratio is not constant. In particular, it's not 1. I mean, if the circular motion temperature was the linear acceleration temperature, then you'd expect you get a plane here, and you don't get a plane. Something interesting is happening. What is it that's happening? Let me make those pictures slightly smaller. Okay, and then think what's happening. Well, so it's let's consider 3 plus 1. It's not 1, but if you look at the numbers, it's not too far from 1 anywhere either. I mean, and you can back this up by now considering various limits. The bottom line is in 3 plus 1, this is a number of order unity, more or less, over the configuration space. And there's a slight bump over there, but it's more or less of order 1. 2 plus 1, well, highly similar. But there's a place where something interesting is happening. Something seems to be going 0. And in fact, it does go to 0 there linearly. And in the picture, it looks like there's a small gap over there, but that's because my numerical plot doesn't extend all that far. So there really is 0. So if the energy in 2 plus 1, things do go different if you've got a really small gap. The temperature is significantly lower than what you'd expect from linear acceleration. You can put more flesh into these observations. I mean, the ultra-relativistic limit, which probably we'd like to do in the experiment, that was considered in the 90s, and you can, yeah, so this blue curve, this is the ultra-relativistic limit found by these people. And in, so this in 3 plus 1, in 2 plus 1, basically similar story, except at very low gap, where again you have something much, much less. So 2 plus 1 is different in the relativistic setting. Non-relativistic setting. So now I need to put the gamma factors in. I'll do similar plots. Okay, and I'll put hats here to indicate that it's now the non-relativistic setting with the gamma factors in, and I'm using the normalization here in the sort of the non-relativistic acceleration rather than relativistic acceleration and so on. But with that being said, the plots look pretty similar. In fact, they are pretty similar. There are some technical differences, okay? Right, so basically this is basically the same. Some minor technical differences. In 2 plus 1 dimensions, again you go to 0 linearly. Okay. Now look at this 2 plus 1 plot over here. So you look down. My numerics went bad at velocity is 0.95. I had difficulty getting the numerics higher, but when I get to 0.95 velocity, I mean, it sort of looks like you're at the, just looking into a precipice. And that's true. In the 3 plus 1 case, it stays constant over there. In fact, it stays 0.9. The number is pretty close to 1. But here in lower dimensions, in 2 plus 1, if you go back here, the ratio, it drops to 0. Fairly slowly, logarithmically, in 1 over log of the gamma factor, but it does go down to 0. So in 2 plus 1, in this analog space-time system, there are in fact 2 regimes where the linear motion prediction is not good. It's the small gap limit and the ultra-relativistic limit. I should emphasize as the last point about this overhead in that when you work out the circular motion temperature in the ultra-relative, in the near speed of sound limit, I should say, the temperature does go to infinity, but it goes to infinity slower than you would think by the linear motion prediction. So the ultra-relativist, the near sonic regime is still a regime where you expect a strong effect, but it's not going to be as strong as you might have thought. And I'm probably way over the 5 minutes, this is my concluding overhead. So I've looked at this circular motion unroot temperature using a quantum dot as my device, both in relativistic and analog setting, and as a measure of the temperature. I've used a detailed balance definition of the temperature. And outcomes, so if you have a 3+1 system, you've got order of unity factor between the linear motion prediction and the actual circular motion temperature, both in the relativistic system and in the analog system. In 2+1 dimensions, same thing over, in a sense, most of the parameter space, but at small energy gap, you have a difference. And in the analog gap, also in the near-sonic limit, the temperature is not as high as you might have thought. Right, so where next? So you could now look at the various things that we haven't considered using this quantum dot, like ambient temperature. You can't put a Bose-Einstein condensate to 0 temperature. There's always some ambient temperature. So you can't put it on an infinite plane either. There's some finite size. And then there are some maybe switch on, switch off effects and so on, and that can be looked at, and in fact we are looking at that in Nottingham. But the problem here is, and so this is basically my last point, that you can't order these quantum dots from an online store. So to do an experiment, you would like to do something else. So what would it take to generalize these observations to the experimental proposal that Bill Unruh was describing? Well, certainly more work, but I want to mention one thing that needs to enter that work. Here is a, shall we say, here's a fun fact. If you are in the vacuum in 2+1 dimensions, then these time-like correlations as measured by Whiteman function, they are purely imaginary. I mean, we saw that in a formula earlier, there was a square root. These are purely imaginary. And for this quantum dot, this is a problem. Quantum dot is really a quantum device, and it knows how to deal with the Hermitian operators, even if it has imaginary pieces here. There's no problem. But if you are starting to shine a laser light through this system and then sample correlations that way, this imaginary part is something that will need some thinking in the future. But that is a topic for the future. Sorry about going over time. Thanks for your attention. I will stop here.
Thank you very much, Jorma. Great talk. All right, we open now the turn for questions. If you have questions, please put your hands up using and we get 2 questions that appear simultaneously in my reference frame. So I'm going to just pick randomly. Okay, we have Chris and Rob. So Chris, please, you go first.
Thank you very much, Jorma. So I'm picking up on this fact that in 2+1 dimensions, if you go to a small energy gap, you don't see very much circular temperature. That's a fair statement, right?
Let me put, right. Well, so what I've plotted here is the ratio of the circular motion temperature to the linear motion temperature, or the linear motion prediction adapted to the space-time. The linear motion prediction at this near-sonic limit, it goes to infinity.
Ah, okay.
The circular motion result, it also goes to infinity, but slower. It's the ratio that goes to 0, and that ratio goes to 0 by this 1/log gamma thing.
But I'm thinking of the other end. So when if you fix your velocity and have a small energy gap,
yeah,
then it just straightforwardly goes to 0.
It goes to 0 with a linear slope. I mean, the slope depends on the value of the velocity, but it's linear.
Okay. So then here comes the question, which is that we know in linear motion, if you have a large gap, you might need to wait a very long time for detailed balance to be established.
Very nice, yes.
And so this plot suggests you want to have a large energy gap to see some temperature, and therefore you might have to wait a very long time. Is that something that you've looked at?
We have not looked at. It would certainly be a topic to look at.
Okay, thank you.
All right, so the next question would be from Rob.
Yeah, hi, Jorma. So since you're on that slide, or there was the same one previously, I'm just trying to understand what the parameters are to be clear. So A is the linear acceleration.
This A had, do you want to talk about analog or relativistic?
Well, let's do relativistic first.
Okay. Yeah.
Like, what is the A? I mean, you said it, but I'm still a bit puzzled as to how you're normalizing that. I mean, is that the acceleration? Is that the acceleration in the linear case?
Right. So for the linear case, this A is the acceleration of the linear case. For the circular case, A is the magnitude of the acceleration for vector.
So which A are you using in the figures? Because you're taking a ratio. Was it the linear A or are you setting them to be the same? Like
I'm setting them to be the same. So I'm comparing them at the same value of the acceleration, so value of norm of the acceleration for vector.
So just to be, so in other words, you've got a velocity V. In the circular case, you'll have, I mean, thinking non-relativistic, the acceleration's V squared over R, and then you set that to be the linear acceleration, basically.
Yeah.
And then that's the A that's used in the comparison. Okay.
Yeah.
So again, I mean, on the one end, you say they're order unity, but I'm a bit surprised as to why you're saying the larger gaps. You seem to think they're not all that interesting, but there's more structure there, right? I mean, there's max and min. I mean, a factor of 3. I mean, it's okay of order unity, but it's a factor of 3. And if the gap were bigger, I assume that's just going to keep going up. But why don't you regard that as?
So it doesn't keep going up. So what we know analytically is that if you fix V, then there's some limit here at small e red, and there's another finite limit at large e red. And I can't remember those limits off the top of my head, but it's something V dependent, and we wrote it in the paper. Now that there is this peak here, it's some sort of intermediate effect at small v and some intermediate value of e. And I admit that I haven't investigated what exactly happens near this peak, but or what the characteristics of the peaking is. But it's some sort of transient effect between small e and large e. The peak doesn't keep going if you go to large and large e with fixed v.
So are you saying it asymptotes or that it peaks and then declines?
It well, so it reaches a finite limit.
So it asymptotes.
Whether there is, it asymptotes to a finite value.
Yeah, okay. All right, thanks.
All right, thank you, Rob. The next question comes from Albert.
Yes, so it's just a small technical question, maybe a couple of slides before. When you write the Weidmann function for the massless field in the two different cases of different space-time dimensions. Yes, so it's just a small technical detail. When you introduce this I epsilon here, naively I would have expected, although there maybe is also a reason why you introduce it for S, but the first thing I would have expected is to have it outside. So XS minus I epsilon to define the Weidmann function. And then you get actually then the commutator part and the anti-commutator part and so on. So
yeah, that's how you start. For this particular trajectory, it's okay to put it there. And I've used that as a shorthand expression over there. To begin with, it's outside and with some time function. And so
right, because then that also has, from the commutator part, well, and I guess from the other as well, maybe, but you even have possibly some divergence that you have to renormalize maybe some quantity.
For this calculation, you don't need to renormalize anything for either of these. If you went beyond first order perturbation theory, then it's a different story. But for this calculation, you're just at the edge of the knife where these expressions.
Because you take the integral to infinity. Okay, I see. Yes. Yeah. Okay, good. Thank you.
All right. Thank you, Albert. I have one quick question, Jorma, which is related to a question that I asked in the past. I just want to hear your take on it. I heard a lot of answers already, but I really always look forward to your thoughts on these things. Now, the zeroth law of thermodynamics tells us that the notion of temperature is defined regardless of the thermometer, right? In the sense that it's a label for equilibrium states. So I typically would think that if I have two thermometers, think in this case, two quantum dots, as you call it here, with different gaps, they will thermalize to the same temperature when put in thermal contact with a very large thermal state, right? Certainly, that's what happens in the linear Unruh effect. No matter what detector I put in, the detector detail balance condition would be independent of the gap of the detector. And I always thought of that as something fundamental because it connects with the notion of thermality as the laws of thermodynamics introduce, right? In the circular motion, this is not the case. Different thermometers, and by that I mean you have different lines in the thermometer, different gaps, different thermometers would actually go to a different temperature. I personally would have thought that that is less of a thermal thing. Of course, we had already discussions as to why maybe people don't agree with that. I want to hear your thoughts about it, John, if that's okay.
Right. So, in a KMS state, this temperature defined in terms of the ratio, it is indeed independent of energy. So there's a characteristic of a KMS state, and that we are not finding an E independent temperature here means we don't have a KMS state. Okay? And in fact, there is a long history going back to, I think, 80s, but possibly even late 70s, asking, could you think of this circular motion effect in terms of a rotating vacuum? Could you think of it in terms of Bogoliubov transformations? And the consensus in the literature appears to be that it just doesn't work. So if you try to build up something like a rotating frame, if you go far enough from the center, that frame goes supersonic, and the usual framework just doesn't work. So a rotating quantum vacuum description of this phenomenon, to my knowledge, it just doesn't exist. One piece of evidence for that is that the temperature is energy dependent. How worried should you be about it? Well, you really are interested in knowing what your quantum dot does, if you happen to buy one. If you can't describe that in terms of a uniform constant temperature, I'm personally not very worried about it.
Okay. The one thing that the one thing is whether we place a lot of importance in the notion of thermality, even without KMS, right? Sometimes you don't have a KMS state, but it's indistinguishable, the result from a KMS state. That could happen. We have a study on something called the Unruh effect without thermality, where we study how a detector can thermalize independently of the gap, even without a KMS state, right? For me personally, I feel that the fact that different thermometers thermalize at different temperatures is not great. But then again, this is me because I maybe place more importance in the notion of thermality. but I, as long as we all agree, right, that is different. There's something about the KMS case or near KMS cases if you want, that all thermometers will thermalize. There's something very fundamental, regardless of your detector, you will see thermalization, right? And this is slightly different. You would see, you would certainly see excitations in the vacuum, and the detector looks locally thermal, but different thermometers would disagree on the temperature. No? That's a fair statement, no? All right. Okay, well, thank you, Jorma. Happy to hear your thoughts about it.
Thank you very much.
Any more questions? Oh, Thales or Rick?
Yeah, so now that you said it, Jorma, regarding the quantization of the field and trying to describe this circular under effect in terms of a Bogoliubov transformation logic and things like this, isn't it not possible to handle this by considering a cylindrical cavity or something like this and imposing boundary conditions for the quantum field and then essentially neglecting the supersonic part?
Right. So so in a cylindrical cavity, you can set up a rotating vacuum, provided the rotation is so slow that it does not go supersonic anywhere. So that's good news. Bad news, your rotating vacuum coincides with the usual vacuum. It's not anything new. If your cavity, if you set up, if you try to make the vacuum rotate quicker than, so quickly that the outer parts somewhere near the boundary, you would be supersonic, then you've got the same problems that you have in infinite space.
All right, thank you.
All right, any more questions for Jorma?
So this, Jorma, this statement you made now about the fact that the vacuum that you get is actually the same. That is it related somehow naively to the fact that one way of intuitively thinking about these rotations is as if you take constant radius and you take that cylinder in space-time for constant radius, and so this is just the geometry. You take this subspace of space-time and you have this constant radius cylinder of space-time, where you have the word line of your detector in this case, and now you unfold it, then basically the relation between a static detector at non-rotating one at constant radius and the rotating one at constant radius, when you unfold it, is the same kind of relation that you have between two different inertial detectors in Minkowski spacetime. Of course, this is just at constant radius. So you have to make sure that the radial contribution here, and it does give rise to non-trivial things, like for example, the fact that you cannot have global synchronization because of the non-trivial. But I was wondering whether this result that you were quoting is somehow, one could interpret it as being partly related to this observation, that it has some similarities to just different inertial detectors in Minkowski spacetime.
Yeah.
All right.
Okay, thanks.
All right, thank you. Anything else for Jorma? If not, let's thank Jorma again. Jorma, as usual, great talk. Thank you very much. All right, the next speaker of the session is David Kubitnak at the Perimeter Institute, and he's going to talk about quantum detection of inertial frame dragging. David, whenever you want.
Thank you so much, and thanks the organizers for giving me the opportunity to present this talk here. So this talk will be also about rotations, but it will be very different kind of rotation. It will be basically rotation with respect to the distant stars. All right, so what is a frame dragging, or also known as gravitomagnetism? So it is a general relativistic effect, which is due to the motion and in particular rotation of matter or gravitational waves. And in many respects, frame dragging is very analogous to electromagnetic induction. Also known as Lenz steering effect, it actually goes back to the early age of general relativity, so to 1918. So let us consider a rotating body with angular momentum J, and let us shoot some radial geodesics at it. So for example, in the equatorial plane. So then what you will find is that actually these radially infalling geodesics experience some kind of Coriolis type force. So if you look at the acceleration in the phi direction, this is precisely governed by the following radially dependent omega. So if omega were constant, this would be just the standard Coriolis force in the rotating frame. But now this omega, of course, depends how far I'm away from the rotating body. But anyway, there's this type of Coriolis force. So in other words, these particles which fall radially in will be dragged along the rotation of the body. So similarly, another effect would be the gyroscope recession. So we can understand it very simply in terms of the electromagnetism. So you know that if you had a charged rotating sphere, then this charged rotating sphere would produce some kind of magnetic field. And of course, if you had a particle with magnetic dipole moment, then there will be a lot more precession around this magnetic field. So now the same thing happens in gravitomagnetism, except now we have gravitomagnetic field instead of the magnetic one. And then we have the spinning particle. And so again, there will be like a precession of the spinning particle or of the gyroscope around this gravitomagnetic field. People may be more familiar with actually extremal manifestation of frame dragging, which happens in the vicinity of rotating black holes. So we know that there is an ergosphere outside of the event horizon, and we know that any particle which gets into this ergosphere cannot actually stay static with respect to distant stars. It has to corrotate with the black hole. So this is like an extreme manifestation of frame dragging. Now, frame dragging has many astrophysical applications. So let me name a few. So for example, there is so-called Bardeen-Peterson effect. And so basically what happens is that if you start with an accretion disk around a rotating black hole, where the angular momentum of the accretion disk is not aligned with the spin of the black hole, then there is a torque on this accretion disk. And after some time, what will happen is that precisely the accretion disk will align with the black hole spin axis due to this torque. There is a possibility of observing this, gravitomagnetism. So we may consider the supermassive black hole in the center of our galaxy, and so then we may observe the stars orbiting around it before they actually merge in, and then we could in principle observe the precession of the orbits of these stars. So that's a possibility of observing this frame dragging in real astrophysical setting. I think it's also related to the production of jets around black holes. So basically you have to somehow extract the energy of the rotating black hole to produce the jets. And again, this is related basically to frame dragging and gravitomagnetism. So now, has this been experimentally verified? Yes, it has. And the result is actually relatively recent. It's this famous Gravity Probe B experiment, which took almost 50 years to complete. When finally, the satellite was launched in 2004, and the final results were published in this PRL in 2011. So what was it? So we have our Earth, and then we launch a satellite at this distance from the Earth, and we launch it so that it actually goes across the northern and southern pole. And so then what we observe is two effects. So there's a big effect, which is the geodesic effect, which is basically like, well, both effects are caused by the parallel transport, but the geodesic effect is basically due to the curvature of the Earth, right? So you know that if you parallel transport a vector along a closed loop, then it can actually rotate. And so this is precisely this geodesic effect, which is in this direction here. So now why they launch it over the north and south pole is precisely that, the two effects, the dragging effect, which is caused by the rotation of the Earth and basically causes the gyroscope to tilt along the rotation, is perpendicular to the geodesic effect. And why is that? Because of course, one of them is much, much bigger. So here's the predicted value. This is milli arc seconds per year. And so the predicted value for the geodesic recession due to the curvature of the Earth is about 6,000, but frame dragging is much, much smaller. It's about 40. And this is what they indeed really measured. And you see that it's consistent. So this is basically like the first experimental verification of this frame dragging of general relativity. So now what is my aim of this talk is to basically provide a toy model for quantum detection of this frame dragging. And so how we shall do it is that I will consider a rotating shell, which is hollow. So it's just it's a spherical shell. And so I will require that this shell is actually flat inside. You can do it, and so that will simplify our calculations. But due to the rotation of the shell, there will be some dragging with respect to distant stars. So basically, the interior is flat, Minkowski space, and moreover, it is dragged with respect to the distant stars. So now what we will do is that we will place an unroot Debit detector inside this shell, and it will be such that basically it is inertial detector inside the shell, but rotating with respect to these distant stars. And then the question is, can this detector actually detect the presence of the rotating shell, and can it detect this frame dragging? And theoretically, yes, and it actually happens in timescales which are much shorter than for a classical signal, which would travel from the detector to the shell and back. Okay, so that's because of this thermality of the quantum field and stuff like that. So anyway, so the talk is based on these two papers, which, however, are basically like a trivial generalization of the paper from a couple of years ago by Keys and Eduardo and Rob, where they basically studied the same situation, placing the unroot Debit detector inside the shell, but in their case, the shell was not rotating, and so it was rather like a probe, non-local probe of the space-time. So here we are really interested in, can we detect this frame dragging here? All right, so let us do it. So let me first, give you the mathematical setup of the slowly rotating shell. So what we will do is that we will take the shell of radius capital R and of mass m, and then outside of the shell, we will consider Kerr spacetime to the linear order in A. So at this linear order in A, basically there is no horizon. Well, we will take the shell much bigger than the Schwarzschild radius or whatever, so there will be no horizon. But to the linear order in A, there's also no ergosphere there. So anyway, so this is the metric. It's just Kerr to linear order in A. You see that there's also A squared terms, which I will neglect later on. But this is Kerr to linear order in A. So that's outside of the shell, and of course it solves the vacuum Einstein equations to the linear order in A. And then inside, I will match the outside spacetime to the inside one, which is over here. So if you look at the induced metric on the shell, where small r equals to capital R, then the two metrics, of course, match as they have two. But there will be some jump in the extrinsic curvatures of the two metrics, and this will be precisely related by the junction conditions to the energy momentum of the shell. Okay, but now if you look at the metric inside, something miraculous happened here. So if I introduce a new coordinate, where basically I introduce this new phi, which is a combination of this thing here, then you see that apart from this constant redshift factor here, the metric inside is manifestly flat, right? So I have a flat metric inside, then I have Kerr outside, I have some energy momentum for the shell. But you see the beauty of this. So if I consider lines of constant phi, which is precisely the Minkowski phi, then this is rotating with respect to the phi outside, which is related to the distant stars. So the interior is rotating precisely, with this omega with respect to the distant stars. So let me just show you this picture over here. So we have the distant stars. And of course, we have the rotating shell of the radius r, and then of course the rotation falls off and it vanishes for the distant stars if we are outside. But if you are inside, there's a constant rotation with respect to these distant stars. But interestingly, it's precisely those observers who are rotating with this velocity omega that are inertial inside the shell. And so that is the key point. So by the way, just a curiosity. So if we want, the inside to rotate at this velocity omega, then we actually have to, produce a shell which is perfect fluid spherical shell, but which rotates with this omega, which is different from that. And so the actual shell rotates in a different speed, and the inside is only partially dragged. And that is true for radius bigger than Schwarzschild radius. If we actually take the limit, capital R goes to 2m, so we are going to the Schwarzschild limit, then the two would coincide and the inside would be perfectly dragged. Okay. So anyway, so now we have the setup of the shell. So let us study the scalar field inside the shell. So we have boson psi and massless scalar field, boson psi equal to 0. So what is super nice is that to the linear order in A, which we are working we can still expand this field in spherical harmonics. And so this is our expansion here. And then we get some equation for this psi. And so this equation will be different, well, inside the shell and outside the shell. So inside, super simple because it's just a flat space. And so our solution for inside is the Bessel function. Of course, I require the regularity in the origin here. And you see that this Bessel function here, it depends on the rotation parameter A. But yeah, okay, so it depends on the rotation parameter A. So now I have solution outside, which has to be matched to the one inside. But outside I have care. So the solution is quite complicated and has to be given numerically. Of course, what is true is that the solution is continuous across the shell, but the derivatives are not. So this thing here is a projection of the psi in the radial direction in the orthonormal frame. But what happens is that this orthonormal frame has a jump. This has a discontinuity as I go from inside the shell to outside of the shell, and that's why the psi will have a discontinuity. So anyway, so I know perfectly well the solution inside. So I know what is the initial solution for my numerical solution of the corresponding psi equation outside, and I know what the derivatives on the shell is from this jump condition here. So I can find the solution outside numerically. In the end, I have to properly normalize this solution, and of course, this is normalized with respect to the Klein-Gordon product, and so there will be some prefactor A omega LM standing in front of this solution here. All right, so that's the modes for the scalar field. So I've decomposed the scalar field into these modes, and now I just place the Unruh David detector inside the shell. So I don't need to introduce this interaction Hamiltonian here. So the only difference to what people have been considering most of the time is that they have been taking the switching on function to be the simplest possible switching on function. So the detector was basically switched on by the Gaussian. And so, strictly speaking, it was switched on for infinite time because the Gaussian never dies. So instead, because we are really interested, for how long we need to switch on the detector inside the shell so that it can still detect things, and we have chosen this cosine to the 4 profile with the compact support given by this parameter eta. So let's just look at how this compares to the Gaussian one. So for example, if I choose this parameter eta here, 1.2, then the Gaussian parameter sigma, which as you have the Gaussian thing, would be given by something by this number here over eta. But this is the comparison. So the Gaussian is the red line, and of course it's switched on for infinite time. The cosine actually dies off it, it is eta 1.2 or minus 1.2 over here. And so we have compared these two things so that the integral profile is the same. So in other words, that the area below these curves is the same. Okay, so that's how we compare these things. Anyway, so we have compact support for the detector, and then we proceed in the standard way. So this is the probability of the transition from one level to the other of the Unruh David detector, and of course it's given by our Weidmann function. And this Weidmann function will correspond to the field, which will be in vacuum. So there's no thermal state. We just everything is in vacuum. And of course we need to evaluate this Weidmann function along the detector's trajectory, and it's simply given by these expansion modes, which we calculated before, but now evaluated in one time of the detector and then later time of the detector here. So we consider the Unruh David detector, which is inertial inside, so rotating with respect to distant stars. And so that means that we are choosing this phi equal to 0. But of course, that means that from the point of view of the stars, the detector is rotating according to this phi here. Okay, and then we place the detector at the distance RD from the center of the shell, because if you actually were in the middle of the shell, you would not be able to detect anything. So that's why we we choose this non-trivial displacement from the center of the shell. All right, so now results. So you saw that.
David,
Oh, thank you, perfect. Okay, maybe I'll speed up then. So that's the response function, and you see that the dependence on the rotation of the shell depends in 3 places. It depends on the Fourier transform of the switching on function. It depends on this b omega, which we saw before, but it also depends on this normalization. Okay, so it enters these 3 places. Okay, so here's the result. So here we plot the detector's response, and we plot, the difference between when the shell is static and when the shell is rotating, depending on the gap of the detector. So if omega is positive, then we actually excite up. If omega is negative, then we actually de-excite the detector. And so here are the parameters which we plot for. But what we made sure is that basically, the travel time from the detector to the shell and back is actually larger than the switching on of the function, than the switching function of the detector. So already the detector is switched for much shorter time than for a classical signal to travel to the detector and back. So now you see, the difference is of the order 10 to minus 5, and for the negative values of omega, and of the order 10 to minus 7 for the positive orders of omega. So now this is interesting to just compare to how the static detector with respect to the Minkowski vacuum would look like, and you see that this is also of the order 10 to minus 5. So in other words, the effect for positive omega is approximately 100 times smaller, detecting the rotation of the shell than for the negative values. All right, we can also plot, how the results depend on the radius where we place the detector. So if we go, so this is the center of the shell, and then we can move the detector all the way to the shell. And you see there's an ideal placement of the detector here, but unfortunately for this ideal placement, at least for the studied cases, actually the classical signal will travel faster than that. All right. So now we have presented the results, at least in principle, this is observable. It is approximately 100 times smaller than just the detection of the shell, but okay. But there's a problem, and the problem is that we have chosen our description to be vacuum solution of Einstein equations only to the linear order in A. But what I haven't told you, but what is quite simple to show, is that the effect which I presented for you is actually at the order of A square, and this is due to the fact that we sum over the magnetic number m, and so the linear order actually vanishes. So now some of my co-authors try to argue that as long as this dimensionless ratio is actually small, then the higher order correction should be small. I'm not actually quite convinced about that, but there are other alternatives what we can do. And so the alternatives is to consider the whole thing simply as a kinematic effect. So so this dragging has nothing to do whether your space-time is really a solution of Einstein equations or not. So in principle, we can take this metric which I presented to be an exact metric, and there will be some T mu outside of the shell, but that's fine. So similarly, you could consider this in analog spacetimes, and it will be fine. So all this, what I'm saying here, is kinematic effect, and we don't really need to care whether the solution is solution of Einstein equations or not. The other possibility is to use exact shells to higher order in A, and surprisingly, these have been constructed to any order in A. Unfortunately, they are quite ugly, and so the shells are. So if you want to keep the inside flat, and the outside vacuum solution of Einstein equations, then you run into a problem that the shell cannot be spherical anymore, and it cannot be rigidly rotating, and it's been shown in these papers. So basically, then you have to deal with general wild class of metrics, and so you cannot separate variables in your modes and stuff like that. So you need full numerics. But anyway, so that's one way to go if you want to do full numerics here, and still preserve the Einstein equations. The other possibility is actually much more nicer, and it's to consider cylinders. So if you consider an infinite cylinder which is rotating, then it only depends on the radius away from the cylinder, right? And so the metric is true to any order in A. the solution is trivially separable because it only depends on how far we are from the cylinder. Of course, the price to pay is that the cylinder is not asymptotically flat, really. So you have some weird fall off at infinity, and the rotation may screw up things. But this has been already considered by Davies and et al. In 1960. And so what they do is that basically they don't go to infinity, but they consider a counter-rotating cylinder. So what's happening here is that we place the detector inside one cylinder. There will be a dragging with respect to the distant stars. Outside of the cylinder, there may be some curvature or not, but there will definitely be a conicity. So there'll be conical deficit. But in order not to deal with the asymptotics at the distant stars, we can place another counter-rotating cylinder. And so just consider the solution, basically here. Okay, so this is work in progress. So we really want to do, the frame dragging in this setup. In the meantime, we just look at the, quantum detection of conicity. So we place the detector here, and we were asking, can we detect the fact that actually there is some conical deficit outside of the cylinder? And that's published in this paper. All right, so to summarize, so inertial frame dragging is one of the fundamental predictions of general relativity. And surprisingly, it has only been actually observed recently by classical observations since 2011 by this gravity probe B experiment. So here we have just shown a toy example of slowly rotating shell, how at least in principle, we could also detect this by quantum observation using the Unruh-David detector. And so this is despite the fact that the Unruh-David detector inside is actually inertial and it lives in the flat space. And it happens on the time scales, which are actually much shorter than the classical detection of the shell proceed. Okay, so that's good. And so the results can also be extended to arbitrary order in rotation parameter, either using cylinders, which is work in progress, hopefully it will come out soon, or by treating these shells to higher orders in A, but that would require full numerical treatment. All right, so thank you so much.
All right, thank you very much, David. Good talk. Please, questions, as usual, put your hands up. Okay, Erickson, go ahead.
David, very nice talk. I just want to ask something kind of stupid, I guess. So because the junction condition, people always naturally, or at least the ones I heard the most, is that you naturally match the inside with flat and then something else outside, right? So is there no easy solutions where your shell is inside not flat, but nonetheless simple enough?
This is very good question. Of course, what we liked is the flat, because then we can do it easily, right? So what we really need for our calculation is to know the solution inside. And if we have, everything is flat inside, then we really simplified our life. So now if you took, I don't know, yeah, it would get much more complicated if you departed from flatness inside, I would say. And then it would not be clear, what kind of trajectories or whatever you would consider. Because, what is really beautiful here is that because the inside is flat, but because our detectors are inertial, classically, they would not see anything by the equivalence principle. Or they would not see anything, right? So it's completely Minkowski space. The detector is Minkowski. Everything is, there's no inertial forces, nothing like that. So this is a perfect setup for that, right?
Yeah, and just one clarifying question. So earlier at the beginning, you were talking about the land stirring metric, right? But in the second half, you're talking about the first order linear expansion of the Kerr metric. Is the first order linear correction turns out to be the same as the land stirring?
Well, that's a good question. I don't know. So the metric, I would say, is different. So certainly, yeah, I think
like the one that rotates like the Earth's exterior, right? That's land stirring, but not linear Kerr, right? Or I forgot one of them, right? I don't know. Will that matter?
Well, I don't think it matters. So of course, what we are talking about here is the axisymmetric spacetimes in some sense, and there is absolutely no uniqueness of axisymmetric spacetimes, right? So you can have so many axisymmetric spacetimes. So I'm not sure whether to the linear order in A is the same spacetime, but in general, I would not expect that it has to be. Okay. So yeah. So but it's a good question. I should find out.
All right, thank you very much, Erickson. I have a quick question. It's very, I don't know, it's more like on the technical side. When you were doing these calculations of the results are evaluated numerically, as from the sum and the integral that you presented. How difficult is it to do the sum for higher harmonics, and how's the convergence of that? Does it converge fast? How many L modes do you need to sum?
So thank you for that question. So I cannot answer that question, but so when Kong did all the calculations, and I think we checked the convergence there, but when do you want to comment on this, or is she here?
I don't see it. Yeah, there we go.
I cannot remember how many L's we need to do. I think it's included in the paper, maybe around 10 L's. Yeah.
All right. Yeah, thank you. It's just because those things are so difficult to treat numerically. I'm always curious. This is more my curiosity than anything else. Thank you. There's another question coming from Albert.
Yes, I mean, I think you just mentioned in the talk, but since it was maybe a little bit quick, it's just to make sure. So you were emphasizing the comparison, considering short times, so shorter than the light crossing time. But
Yeah.
And then if I got it correctly, maybe not surprisingly, the effect that you find here then is about the 100th of what you would get just from the switch on and switch off in Minkowski, non-rotating Minkowski spacetime, right? So
Sorry. So okay. So I'm not sure. So if you look at so this is the difference between the response function of Minkowski and the static case.
Yes.
And so you see that it's of the order 10 to minus 5 or something like that. So if I'm looking at the static with respect to Minkowski, it's of the order 10 to minus 5.
Right.
So now if I'm looking at the difference between the static and the rotating, okay. So then if you look at the positive omega, so that means that you are trying to excite the detector, then it is of the order 10 to minus 7. Okay. So for example, for omega equal to 1, then it's of the 10 to minus 7. So it's basically 100 times smaller, right? So basically, like, I can detect the rotation of the shell, but for positive omega, it would be 100 times smaller effect than actually the detection of the shell itself. However, if you look at the negative omega, so we are trying to de-excite the detector, so then it is sort of of the order 10 to minus 5. Okay, so in other words, if I'm trying to de-excite the detector, the two effects are approximately comparable. I don't know, does that answer your question, or?
Well, it is in the direction, in the sense that, of course, theoretically you find that it's possible. It's just more surprised. It's just the point that the fact that you try to do it in such short times. So then the natural first reaction, and that's what you analyze here, partly is that, okay, if I switch on and switch off my detector rather fast, even in trivial flat space, I will get a non-trivial effect. And that's what you are, of course, comparing here.
Yes, exactly. Yeah.
So it's relevant. And what I'm kind of, at least from maybe the right-hand side part of this plot, is that it's 100 times smaller. So it would be challenging, not just because maybe the effect is small, but it's also because the effect that you're interested in is 100th of the other effect that is dominating. So what would make it in practice experimentally hard is that the effect is maybe small, but it's also that you have another effect which is 100 times larger than is masking what you're looking for.
Yeah. It's a very good point. So maybe there's a way how to decouple these two effects. Maybe not. But this was beautiful, right? Because here, in this classical experiment, we could really decouple the traditional geodesic effect, which is, I don't know, what is it, 40 and 6,000? Is it 100 times? Well, maybe. So it's 100 times bigger. The geodesic effect is 100 times bigger than the frame dragging, right? But here, I could decouple them because one is perpendicular. Well, they are perpendicular effects in this setup, right? So maybe there's a way how to do this. I don't know.
You need to come up with
I doubt it, but
you would distinguish. Yeah. Mm-hmm.
Yeah. I'm not sure. It's a good point. Yeah. How would you decouple these two?
Okay. Thanks.
All right. Thank you very much, Robert. Are there any more questions? If there aren't any more questions, let's thank David again. David, thank you very much. Great talk.
Thank you.
Right. Our next speaker is Christian Klein from the University of Leipzig. And she's going to talk about quantum fields and strong cosmic censorship. Christiane, whenever you want, floor is yours.
Yeah, thank you very much for this kind introduction. And also thanks to the organizers for this opportunity to speak here today. As already mentioned, I'm going to talk about strong cosmic censorship and what happens if you bring quantum fields into the picture. So it's a little bit of a different topic to what we've had so far. And it's based on this paper here by me, Stefan Hollands, and Johansson. Okay. So let me give you a brief outline of what I'm going to speak about today. I will first give you a short introduction into strong cosmic censorship, the classical story. I will then tell you what happens if you introduce quantum fields into this picture. The third and fourth section will be the main results of our work. And then finally, I will give you a summary and hopefully also a short outlook on some more recent results. Okay, so let's start with a classical story. So the basic idea to discuss the basic idea of strong cosmic censorship, let us consider the Reissner-Nordström spacetime. So a spacetime which is asymptotically flat and which contains a charged black hole made up of these regions 2 and 4 over here, which are separated by a horizon. And we also have this exterior region 1, which then has this asymptotically flat region here. And now imagine we know everything that we have to know, so all the initial data on this green surface here, which is a Cauchy surface for the regions 1 and 2. Then by solving some differential equations, we can determine everything that happens in part 1 and part 2 of our spacetime. However, things become very different once we cross into region 4, because then any kind of signals that might or might not come from the wiggled line here, which represents the singularity in the middle of the black hole, can reach us. And since we have not really any clue what kind of boundary conditions to put there, we, in this sense, lose determinism once we cross the Cauchy horizon. That sounds a bit troubling. However, already in the 70s, Penrose found a heuristic argument why this should not be a problem. Namely, consider you have 2 observers, here depicted by the red and the blue line. And one of them, red, is staying outside of the black hole. And during the infinite amount of proper time that he takes to cross this exterior region, he will send signals to the second observer at some constant frequency. The second observer, however, is falling into the black hole and in a finite amount of proper time reaches the Cauchy horizon. So for him, it will seem that the signals coming from red will be more and more frequent as he approaches this horizon. And this is not only true for signals sent from A to B, but for all sorts of wave-like perturbations that you can put on this space-time. They will be infinitely blue shifted as they approach this horizon. And in turn, the energy momentum tensor that is associated with such perturbations will also become very large, close to this horizon, and by back reaction cause a large curvature. So in some sense, it will be impossible for the observer to cross this horizon. And this is exactly the idea of the strong cosmic censorship conjecture, of which there are a variety of concrete formulations. Here we will work with one due to Christodoulou, which states that for generic initial data on some Cauchy surface, where generic still means smooth, the metric should be inextendable as a H1 log function across the Cauchy horizon. What that means is that its Christoffel symbols at the Cauchy horizon should become locally not square integrable, and thus the metric cannot be extended as a solution to the Einstein equations, not even as a weak solution. More recently, Hinz and Vagi have found that violation of strong cosmic censorship happens if this coefficient beta becomes larger than 1/2, where the denominator of this beta is nothing but the surface gravity at the Cauchy horizon, while the numerator is the decay rate of the slowest decaying quasi-normal mode of the black hole. So imagine you're disturbing your black hole a little bit. It will then ring at some eigenfrequencies, and this ringing will decay at some rate. And the slowest of these rates is then alpha. However, we are not that interested in the Reissner-Nordström spacetime, but rather in Reissner-Nordström de Sitter, where you also have a cosmological constant, which is positive and non-zero. And as you can already see from this f of r in the metric, we then have the possibility of not 2, but 3 different horizons, namely the horizon, inner horizon of the black hole we had before, which we will also call a Cauchy horizon from here on, and the outer horizon of the black hole, or the event horizon. And now we also have the cosmological horizon. We also get an additional effect on the perturbations on our space-time, namely the cosmological redshift, which counteracts the blue shift. So the perturbations will decay quicker, and so whether strong cosmic censorship is violated or not becomes a much more interesting question. And indeed, by numerically studying such quasi-normal modes, Cardoso et al. Have found that the strong cosmic censorship in the linear picture is violated by classical real scalar perturbation if the charge of this black hole, which is in the space-time, is large enough. So what happens if we introduce quantum fields into the picture? That is exactly the questions that Hollands et al. Asked in their paper last year. And to answer this question, they considered the energy flux towards the Cauchy horizon of a real scalar quantum field in a state that is Hadamard around some Cauchy surface of the regions 1, 2, and 3. What this condition means is just that in these regions 1, 2, and 3, this should be some physically reasonable state. And they found that in the Kruskal type coordinates, so some coordinate that extends through the Cauchy horizon and places it at v equals 0, this energy flux in any of these Hadamard states, initially Hadamard states, has a quadratic divergence. And there are some subleading terms which contain the state dependence. And this prefactor C can be expressed as a series in angular momentum, an integral over frequencies, and then some integrand, which depends on the scattering coefficients of the so-called up modes. And to give you a more precise definition of these up modes, let's do a brief excursion on the dynamics of the scalar field we are considering. So the scalar field is described by the Klein-Gordon equation, where box G is just the D'Alembert for this Reisner-Nordström de Sitter spacetime, and mu is a mass parameter, where we can also put any kind of non-minimal coupling, since the Ricci scalar for the Reisner-Nordström de Sitter spacetime is constant. We then make a mode ansatz, where we handle the angular part by spherical harmonics, and are left with an unknown radial function that satisfies the following equation. Here R star is the so-called tortoise radial coordinate. All we need to know here is that it goes to plus minus infinity near the horizons. And W of R, our potential, actually decays exponentially in terms of this R star, as R star goes to plus or minus infinity. So what we have here is a one-dimensional scattering problem with a localized potential. So we would expect to find solutions that asymptotically in R star behave as free waves. And one kind of these solutions are exactly the up modes, namely the one that originate from the event horizon. There are two sets, one in region 1 and one in region 2. And after coming from here, they can be either scattered off the gravitational potential, or they can be transmitted. And note that in region 2, our star coordinate actually goes upwards, so that both the transmitted and the scattered term appear for R star to infinity. Okay, so after this short excursion, let's come back to the results on quantum effects on the spacetime. So remember that we are after this energy flux towards the Cauchy horizon, and we found it to be quadratically divergent with a prefactor that is, after summing over angular momentum and integrating over frequency, in the end some function of the scattering coefficients. What this means is that strong cosmic censorship on the Reisner-Nordström de Sitter spacetime, considering real scalar perturbations, holds given that this constant C is generically non-zero. However, in their paper, Hollands et al. Only computed this constant C for a few cases of the conformally coupled scalar. So what we wanted to do is to try and improve the method of calculation for C to really test its behavior more generically. And the way we did this is try and solve the 1D scattering problem locally, meaning that we look at a neighborhood of each of the horizons separately, then calculate the scattering coefficients by comparing our local solutions where they overlap, and finally compute the constant C and try to verify that it is generically non-zero. Okay, so let's start with tackling this one-dimensional scattering problem for the radial function. To do so, we will first, as I said, focus on the neighborhood of one of the horizon, namely this red region here around the event horizon. And following Suzuki et al., change to a variable that is better adapted for dealing with this region. And then we also make an ansatz, which already explicitly contains the kind of asymptotic behavior in our star that we want to have at this horizon. And the left unknown is this function h of x, which satisfies the equation written here. And if this last bit of this equation is absent, the equation has the form of a so-called Hoyne differential equation. And this, we exactly get this Hoyne differential equation in the case of conformal coupling. This is why that case was considered previously. But here we want to also generalize to other masses. We also get boundary conditions for H, namely we demand it to be regular here at the horizon and also normalized to 1. How do we solve H of x? We make a very simple and naive ansatz in a way, namely just the power series. And from the boundary conditions, we then get that we actually only have to take a one-sided series, so only positive powers of x, so that we get a regular function at 0. And we also set h not to 1. If we put this into the differential equation, we find a 5-term recurrence relation for the coefficients, which actually reduces to a 3-term recurrence relation in the case of conformal coupling. And with the help of the boundary conditions, we can use this recurrence relation to uniquely fix all of the Hn by just recursively evaluating this equation. And we can do this on a computer up to some arbitrary high order. And in this way, we get a pretty good approximation of this function h of x. And in turn, a solution, an approximation of a solution to our scattering problem. And then we can repeat the same thing for the other horizons, since up to now we only have a solution in this red region here. And to cover the other horizons, we will repeat the same in some new adapted variables around the cosmological horizon, getting a solution in the green region, and around the Cauchy horizon, getting a solution in the blue region. And finally, we put in some normalization constants. Okay, then how do we get to the scattering coefficients? That is now rather straightforward. We express the up modes, looking at their asymptotic behavior in terms of our local solutions, and then just compare the two definitions that we get by using the two asymptotic behaviors that we have in some regions where our solutions overlap. So there would be this region here or that region here. And then we solve the equation we get for the scattering coefficients. Okay, so then we have everything we need to compute the constant C. So let's see what the results are. First, we can plot it as a function of the charge of the black hole. And what we see here is that, in fact, it is generically non-zero, but it can change its sign. So what this means is that, remember that this constant C was the prefactor of this quadratic divergence, so the strongest divergent term of the stress energy tensor. So considering back reaction, this will mean that if you have some group of geodesics approaching this horizon, depending on the sign of C, they could either be accelerated towards each other or accelerated away from each other, meaning that an observer coming close to this horizon might be either stretched or squeezed to death, depending on the sign of C. And this seems to depend on the space-time parameters. And these results are actually also in very nice agreement with some earlier results on Reisner-Nordström by Silberman et al. We then also plot the dependence on the mass of the scalar field. And here we also have results for different cosmological constants. And here you can see the same picture. Basically, it is generically non-zero, even though it becomes quite small for large masses, with a sign change over here. So again, even if you have all the parameters of your space-time fixed, the final fate of the observer can still depend on the mass of the scalar field that caused the perturbation. Okay, so let me summarize and give you a short outlook. Hollands et al. Studied quantum effects on the strong cosmic censorship on Reisner-Nordström de Sitter. And they found that these can be restored if this constant C, which was the prefactor of the quadratic divergence of this energy flux towards the Cauchy horizon, is generically non-zero. We then took on the task of computing this constant C, and we broke it down to first semi-analytically handling this one-dimensional scattering problem, and then by this analytic reformulation, even reduced this to basically just computing some coefficients in a power series by solving a recursion relation any number of times. We found that at least in the parameter range that we looked at, C seems to be in general non-zero, which means that strong cosmic censorship is restored by the quantum effects on the Reisner-Nordström de Sitter spacetime. However, the sign of this constancy was not fixed, which means that the final fate of an observer approaching this horizon really depends on the parameters of the spacetime and of the scalar field. Okay, I also have a short outlook. Since we are considering a charged black hole, it seems sensible to also consider some charged matter in your model. And for simplicity, we then had a look at what happens if you put charged scalar fields on this Reisner-Nordström de Sitter spacetime. This has also been studied for classical charged scalar field perturbations by different groups. And as far as I'm aware, the latest results there are that there is a small parameter space where these charged scalar field perturbations allow for a violation of strong cosmic censorship. So what we did is calculate again this energy flux towards the Cauchy horizon. But since we have a charged scalar, there's another observable that is interesting to look at, namely the current density. And we also calculated that one near the Cauchy horizon. And I have here a plot from a rather recent paper showing the current density again as a function of the charge of the black hole for different charges of our scalar field for a conformally coupled scalar field. And the surprising thing that we found here is that this function as well changes its sign. So what this means is that contrary to naive expectations where you would, for example, from the pair creation picture, think that quantum effects would always discharge the black hole rather rapidly, it seems that there are some parameter regions where quantum effects can actually do the opposite and charge the interior of the black hole. That is not to say that the black hole charges up. So if you look at the event horizon, everything is always discharging. There is no sign change. But if you look at the Cauchy horizon, we find this interesting sign flip here. So it seems that regarding quantum effects on the charge evolution in the interior of such charged black holes, there is not everything understood yet, and there is still some work to do. So as to fully understand what is going on. Okay, and that's actually the end of my talk. Thank you very much for your attention.
Thank you very much, Christian. All right, we open the floor for questions now. please put your hands up. And I see that there's a hand up. Mark.
Yeah, hi, Christian. Thanks for the talk. This is something that I think you're basically saying implicitly, but I'm not sure you said it explicitly, which is in the classical case, I think the violation of cosmic censorship happened very close to externalities for very particular, very high charge of the black hole. Did you look specifically at those cases? You're talking about restoration of cosmic censorship, but I'm not sure if you.
Yeah, so if you look at the work at Hollands et al., they actually do hold all of their calculation for a region where strong cosmic censorship is classically violated. So where there is this large spectral gap, basically. And not in this plot, but in other plots of this paper, we actually explicitly scan this region up here. That's why there are also more data points, which actually corresponds to this region where this classical strong cosmic censorship violation is found, yes. So that's mostly what we looked at.
Okay, thanks. Just a quick comment as well on the charged field case. I thought there were some certain, you're getting into a region where there are, I think there are instabilities of the space-time, like even outside the space-time.
Yes.
So
in the case of a charged scalar field on the Rising-Notch and Zeta space-time, you have instabilities in the exterior, even in the classical case. But we made sure that these do not occur in the parameter region we're scanning. So as you will notice, our cosmological constant here is rather large. It's actually the largest from the three that we scanned for the real scalar. And this is because for this cosmological constant, we found that in the whole parameter region we looked at, this instability should be absent.
Great, thank you.
All right, thank you very much, Mark. Christian. So next question comes from Rob. Rob, go ahead.
Yeah, hi. I just want to be sure I understand the significance of this. Can you go back a couple of slides, please? Yeah, well, that was it. The next one.
This one.
So it's partly that. Yeah, so you're calculating this coefficient C of the divergence, right?
Yes.
Yeah. So I see all of these curves going through zero. So that does mean there's a region where, I mean, it's finely tuned, I guess, but where the divergence isn't present, and then you could plunge through the Cauchy horizon. Is that right?
Well, yes and no. So this
far
is
left of the
region. This is actually a point. So this really just goes through zero once for each space-time that we choose. So in that sense, it's like I forgot the word. It's a volume zero subspace of your configuration space, so to say, where
so that's right. It's finely tuned, but it nevertheless is present.
Yeah, but even in that case, we are only looking at this one component of the stress energy tensor, which is the one that is expected to diverge most badly. But there are still other components that could also, for example, behave quite bad that we didn't look at. So that might save you in this case. But still, the statement is generically allows for volume zero measures of your parameter space to be excluded. For example, no perturbation at all would also allow you to plunge through the Cauchy horizon, because no perturbation at all is just the Rising-Notch and de Sitter solution, which clearly has this Cauchy horizon.
Well, yeah, that's true. But then I guess it's a matter of how important the divergence is, because you could imagine C being ultra tiny. So there's some finite neighborhood where the divergence has a small coefficient. But I guess the other thing I'm wondering is if you had more than one scalar field, maybe with different masses, right, or lots of them, then I presumably would have a lot of different zeros, right, from each scalar field, and maybe they could perhaps cooperate in some way and then broaden the region a bit beyond a set of measure zero. Is that conceivable?
I'm not sure. I mean, if they are not interacting in any way, I guess you could just add up their stress energy tensors in this way, and that would even lift this zero, because if the one has a zero, then the other might not. And in this way, they could instead cooperate to make sure that whatever you do, you always have this divergence.
Well, I guess you're right. It could go that way, but I'm thinking, could it go the other way, where there's some cooperation between them, where the divergence goes away? But maybe, I don't know, right? I mean, maybe if that's why I'm trying to understand how much one should or should not worry.
I'm not sure how they would do that, actually. I mean, I guess if you had like interacting quantum fields, then you would have to redo this whole thing anyways, because this is for linear fields. So maybe in this case, but I think as far as linear fields go, this shouldn't get worse by putting more different fields onto your spacetime.
Well, okay. I mean, I guess I think that might be worth thinking a little bit about, to see how multiple fields change this problem, maybe for better, maybe for worse. So one other question is, what if you have you ever considered spinor fields and their effects?
We haven't done that so far. I think there are works for the classical perturbation that consider spinor fields, but I'm not entirely sure. So yeah, this would also be some direction one could go in. That was, for example, one thought we had after now more or less finishing this project with the charge scalars, that one direction one could go further is to extend this to spinor fields and to really simulate something like electrons.
Yeah, I think that would be worth thinking about.
So far.
Yeah. Okay, thank you.
You're welcome.
Okay, thank you, Rob. Next question comes from Cisco. Cisco, go ahead.
Hello. Thanks for that talk. I enjoyed it. I was curious, have there been any works about observational implications, or like ways of constraining possible breaks of strong cosmic censorship, just from like looking at the sky?
Not that I'm aware of, but in a sense that would also be kind of difficult, because it mostly concerns the inner horizon of these charged or rotating black holes, as far as I understand. And since they are inside black holes, that seems kind of difficult. I'm actually not aware of any proposal to somehow observe the violations.
I mean, are there any implications for what happens outside of the black hole in question, for instance? Because I mean, sometimes I think, oh, violations of cosmic censorship, they signal the breakdown of trying to understand the universe at all. But other times, if it's just all located inside the event horizon of a black hole, what does the outside universe really care about it? Other than not being able to go through a wormhole, or whatever your favorite flavor of traversal is. Sorry, could you just comment on, do they have any devastating consequences to the rest of the universe?
I'm not sure. I don't really think so. I mean, one thing that you might be able to observe, to maybe make some remarks on this, is the ring down of black holes, where you see these quasi-normal modes. So you can see this spectral gap in a sense, but that's, I think, the closest to get to observing something related with a strong cosmic censorship. Since weak cosmic censorship tells you that these singularities are at least behind one horizon.
Yeah, I'm not sure exactly what the full story is, taking into account everything that we know about quantum field theory and curved space-time, and I haven't been following any of these results, so I was just curious. Thank you, and in particular, thanks for that comment about quasi-normal modes. My group mates work with them a lot, so I'll think about that. Thanks.
Thank you very much, Cisco and Christian. Are there any other questions? If there aren't any, let's thank Christian again. Thank you very much for the great talk, Christian. All right. All right, the last speaker of the session is Alessio Belfiglio, and he from the University of Camerino, and he's going to talk about entanglement in Einstein-Cartan cosmology. Alessio, whenever you want, floor is yours.
Okay, thank you. And thanks for the invitation. So the aim of my presentation is to introduce the notion of entanglement within a modified theory of gravity. That in this case, we studied the Eisencartan theory. That is a theory in which, other than curvature of space-time, we have also torsion. But what is the reason? Why should we introduce torsion in the description of space-time? For this reason, I will first introduce the Eisencartan theory and explain why torsion may have a mathematical but also a physical meaning within gravity. Then we will move to the entanglement characterization in a space-time with torsion. And at the end, I will draw some conclusion and show some future perspectives, so an outlook. So Eisencartan theory is a modified theory of gravity in which the spin of particles, plays a dynamical role. Dynamical in the sense that spin is coupled to a geometric quantity of space-time that is called torsion. In general, the Eisencartan theory has not been experimentally verified yet because it requires, in order to see differences between the Eisencartan and the Einstein theory of relativity, we need to go to very high mass densities that are still small with respect to the Planck density, in which we should consider a quantum theory of gravity, but at the moment are very high, so there are not experimental verification of the theory. Why should we introduce torsion? There are some mathematical reasons, but also some physical implication to the possible introduction of torsion. Concerning the mathematical part, in general, if we introduce torsion and relate it to the spin of particles, so if we assume that spin has a dynamical role in gravity, we are able to obtain the correct generalization of the conservation law for the total angular momentum. So in this case, orbital plus the intrinsics of the spin. At the same time, if we introduce torsion as a geometric quantity that is unrelated to the metric, we can restore the role of the Poincaré group that is very important in the standard model of particle physics, but it's not in general relativity. So if we introduce another geometric element that is torsion in this case, we can restore the role of the Poincaré group. And from the physical point of view, there are several works in which torsion is considered a possible dark matter candidate, and I will come back briefly to this part. So in general, this is the idea that the presence of torsion and the relation between torsion and the spin of particles is able to close this diagram and to introduce, to restore the role of translation, and so of the full Poincaré group in gravity, in the theory of gravity. Okay, just to present briefly the Eisencartan theory. This theory is based on two main assumptions. One is the same as the second one is the same as general relativity, in the sense that covariant derivatives of the metric tensor are set to zero. But the difference is that the affine connections are no longer symmetric while they are in general relativity. And so from here we can see that now the connection is a separate entity with respect to the metric, so they are independent essentially. And the space-time in which we discuss the Eisencartan theory is called the Riemann-Cartan space-time. Okay, so starting from these assumptions, the torsion tensor is defined as the antisymmetric part of the affine connection. Of course, in general relativity, it is zero since the connection is symmetric. And starting from the definition of the torsion tensor, we can write the total affine connection in the Eisencartan theory as the sum of the connection of general relativity plus another term that is named contortion tensor, and of course is related to the torsion tensor here defined. So this is for the Eisencartan theory. The aim of our work, was to try to characterize entanglement in such a space-time, in a space-time that contains not only curvature, so not the space-time of general relativity, but the Riemann-Cartan space-time. Of course, in trying to do this in cosmology, we need to satisfy some constraints that are the constraints of the cosmological principle, so isotropy and homogeneity of space-time. So I will briefly introduce how Riemann-Cartan space-time can be described in a cosmological scenario, and then I will move to the characterization of entanglement for Dirac and Klein-Gordon fields. Okay, so for what concerns the metric, we have assumed a conformally flat Friedmann-Robertson-Walker metric. This is well known in quantum field theory in curved space-time. And as for the scale factor, this is also a well-known form. This scale factor assures that space-time is asymptotically flat in the asymptotic region, so in the in and out regions. And this is fundamental in order to define the notion of particles. And it has three parameters that are A, B, and rho. A and B describe the volume of the universe, and rho the expansion, the rapidity of the expansion of the universe. For what concerns torsion, as I've said, the torsion has to satisfy some constraints in order to be defined in a cosmological scenario. So in a scenario in which we have to respect the cosmological principle. And the most general form for torsion has been found some time ago. And it is based on two independent functions that, of course, can depend only on time, because we have to satisfy the homogeneity of the space-time of the universe. And we can write the torsion tensor and accordingly the contortion tensor in this way. And so we will use these answers for torsion in order to try to characterize, to give an introduction to how entanglement can be characterized in such a framework. So starting from the Dirac field, the Dirac equation in a Riemann-Cartan space-time has this quite complicated form. The first part is the Dirac equation in general relativity, essentially in a curved space-time without torsion. And the last term contains the contortion tensor, so it's related to the presence of torsion. Now, if we assume that the cosmological principle holds, and so we use the previous form for the contortion tensor, this equation simplifies to this one. So it is just the function f that describes torsion and describes the coupling of the Dirac field, so Dirac particles to torsion. Now, this equation cannot be solved analytically for all the values of t, but we have noticed that it is possible to solve it at least in the asymptotic regions. And here are the solutions that in general are quite complicated, because the four component spinors here have a complicated form, while the energy is, of course, is modified by the presence of the torsion field, so of torsion. And in order to try to characterize entanglement, the idea is well known, is the same idea used in general relativity. We have to write the Dirac field operator in the asymptotic regions. So in the first one is for the in region, and the second one for the out regions, where A and B are the annihilation operator of particle and antiparticles. If there is in, is for, of course, the in region, and out for the out regions. In order to try to characterize entanglement, we needed to find the Bogoliubov transformations for the field from the in to the out region. As I've said, since the Dirac equation in presence of torsion cannot be solved analytically for all the values of time, so in this case it's the conformal time, we need to resort to some approximation or some numerical solution. Here I show one approximation that we have done that is related to our work, since this work is related to a paper that I will show you at the end. And we have assumed that during the expansion of the universe, torsion is considered negligible, so it's very small, while in the asymptotic regions, it has this form, whereas it's a generic parameter that then we have taken to be 6. It is an integer value, however. And if we assume this form for torsion, we can derive approximate solution for the Bogoliubov transformation from the in to the out, and so from the out to the in regions. And in general, these coefficients have this form and should be normalized. And here C is taken, of course, it depends on the answers for the scale factor. In this case, this C is related to hypergeometric functions. Using the Bogoliubov transformations that I've shown, one can derive the number of particles created in such a space-time, so in a space-time with torsion, and the difference between the case without torsion and with torsion. And the same can be done for antiparticles, so of course. So as it happens in general relativity, we have a particle-antiparticle creation due to the expansion of space-time. So considering an expanding space-time, if we compare the in and out operators and we compute these expectation values, we see that we have particle creation. And entanglement can be defined accordingly. One has to write the in vacuum in terms of the out states, and in general, it has this form is a complicated form, since we are considering explicitly the spin of particles here. And in order to study entanglement, one has to consider the reduced density operator. So one has to take the partial trace over particles or antiparticles. Here we have taken the trace over antiparticles, and this is the generic expression for the reduced density operator, from which we can compute the von Neumann entropy. That has this form. Here we have assumed that the production of particle and antiparticles with opposite spin is the same. So we have taken, we have introduced the total number density n. And so within this model, with this approximation, we notice that we have a large particle production for small values of the momentum. And here we have taken different values for the torsion function, so for the torsion field. And for the larger is torsion, the higher is particle production in this model. And these are the parameters that we have used in this toy model, essentially. Okay, this is to show that if we increase the mass of our particle, the effects of torsion are not becomes less important in some sense, because if you notice here, there is a small region that is light blue, so increasing the mass of the Dirac field, torsion has a small effect on the entanglement entropy with respect to this case in which the mass was very small, and there is an important effect of torsion for small values of the momentum. And this study can be performed also for the scalar field, so the Klein-Gordon field. Of course, in this case, we do not have a minimal coupling to the field, but we have non-minimal coupling by means of the curvature of space-time. Since we are dealing with a theory with torsion, we need to generalize the notion of a scalar curvature to the case of the Riemann-Cartan space-time. And it has been shown that the most general form for a non-minimal coupling between torsion and the scalar field has this form, where there are 5 arbitrary parameters, coupling parameters. There are this side. While this P... Okay, thanks. While these terms are the torsional components of the Riemann-Cartan curvature, because in this case, the curvature can be written as the sum of 5 terms. The first one is the scalar curvature, the Riemann scalar curvature, and the others are torsional components that I've introduced here. Okay, so in literature, it has been shown that typically there is one contribution that is larger than the other, and it's P4, that has this form and that is related to the torsion tensor. And assuming that this term is much larger than the others, and assuming conformal coupling with the Riemann scalar curvature, one can arrive to this equation. So this Dirac equation in a space-time with torsion. And also in this case, we notice that just only the function f enters in the description of the coupling between the field and the torsion. Yeah, the procedure is the same. Of course, one also in this case can look for approximate solution or also numerical solution. Here we have shown that there is a special behavior, a special answers for torsion for which we can obtain analytical solution. Of course, these answers cannot be true for the expansion of the universe, but for example, it may be useful in some inflationary scenarios, and we are still working on it. But the procedure is the same. One has to write the Klein-Gordon field operator in the in and out regions to compute the Bogoliubov transformation, arrive to the density operator and take the partial trace, so obtain the reduced density operator. And here we show that what is the behavior of entanglement for different values for the coupling parameter psi4. That is the only, as I've said, the only relevant parameter in our model. Also the behavior of entanglement for different values of torsion, so the parameters that describe torsion. Okay, and our conclusion, I present some conclusions and what are the future perspectives of our work. In particular, we have shown that for what concerns the Dirac field, the presence of torsion can increase the amount of entanglement and can drastically modify entanglement for small values of the momentum. While for the Klein-Gordon field, there are slight modifications to not only the amount, but also the mode dependence of entanglement, as I've shown. But in general, since this is a non-minimal coupling with the field, we need larger values for torsion. In general, this behavior of the entanglement probably within the Eisencartan theory, since in this theory torsion is related to spin, we should refine the answers for torsion. And in this case, probably the behavior of torsion for small values of the momentum will not be drastically changed as in the case that I've shown. And in general, another important future perspective is a possible modification for the model of the universe, since in this case we have assumed that the universe is asymptotically flat in the in and out regions. But of course, this does not correspond to the real behavior of the universe in the early phases, at least in the early phases. And in general, there are several studies, as I've shown also this one here, in which torsion is related to dark matter. For what concerns the Dirac field, we have also tried, and we will try in the future, to associate the behavior of entanglement for small values of the momentum to the presence of torsion dark matter. While for what concerns the Klein-Gordon field, it has been shown that a coupling to the Higgs field may give mass to torsion, and so torsion can become a potential dark matter candidate. So this presentation is summarized the results that we have obtained in this paper that we have that you can find on arXiv. And we are working on another paper in which we want to clarify better the role of torsion with respect as a dark matter candidate, both for the Dirac and the Klein-Gordon field, essentially. And thank you. That's all.
All right. Thank you very much, Alessio, for the talk. We open the floor for questions now. Please put your hand up as usual. Right, I don't see any questions. Okay, well, if there aren't any questions, let's thank Alessio again. Alessio, thank you very much.
Thank you.
And please, let's thank all the speakers of this session. Thank you very much for the great talks. And with this, we conclude this 13th session. Remember that we will meet again next week at the same time, 9 a.m. EST. Until then, take care and see you in the next session.